Last time we talked about multivariate normal distributions and the fact that a multivariate normal distribution has a covariance matrix. This time we want to talk about covariance matrices in a little more general context and also the very closely related idea of a correlation matrix. So here we have a piece of data that's kind of fun to look at, and we'll use this to illustrate the points we want to make. This is kind of fun because it's not just the usual featureless scatter plot. What you're seeing here is that each blue plus sign represents a gene in the human genome, and most genes have two or more things that we're going to call introns. I'll tell you what those are biologically on the next slide. And in this graph, I've graphed for each gene the length of its first intron against vertically the length of its second intron. And actually these lengths vary over many orders of magnitude, so this is the log base 10 of these lengths. A value 3 here means that the intron, say here, is of length 1,000, and if we go over here, the second intron of that same gene is of length a little more than 100. Notice that this distribution has kind of hard edges here, and there's actually some biology in that. The question we're going to be interested in, though, is there a significant correlation here? If the first intron is long, does the second intron also tend to be long? Well, you can see that that might be true because there is a kind of a tendency to cluster along the diagonal here, but maybe we're being fooled by the odd shapes of these things separately, by the fact that they have hard edges and so on. What would be a statistical test for whether there is that association between the lengths of the introns? Now I've promised to tell you what an intron is. If we look in the human genome, genes which occur along the genome are often split up into different pieces called exons, which ultimately have to be spliced together before we can make messenger RNA and then make a protein from that gene. So the exon is the useful part of the gene, by and large, and introns, when they occur, as in yellow here, are the part that we have to get rid of. And there's a whole complex piece of machinery in cells that finds the introns and wraps them around into a kind of a lariat shape here, and then splices them out, cuts them off, so that in the end we're left with two exons abutting each other in the way that they're supposed to be. And because this has to make a lariat around these complicated proteins here, there's a minimum length to how long that intron can be. And that's what gives the hard lower bound that was seen in the previous slide, the fact that the introns have to wrap around this big machinery. Of course, as so often in biology, there are exceptions, and if you look at that previous distribution, we'll see it again. There are genes that somehow manage to evade this limit, that have some different splicing mechanism or slightly different trick that they are able to do. It's all very carefully arranged to allow the exons, these blue segments, to be of any length, even quite small. But the result is that evolution favors introns that are at least about 150 or 200 base pairs in length. There are interesting questions in biology as to why this has to be. Why is it so important that we can have short exons, but it's not so important that the intron length be short and that can be essentially regulated to be above 150, 200 base pairs. But back to doing statistics. As I said, the covariance matrix is a more general idea than just how it occurs as a parameter in multivariate normal distributions. If you have any sets of random variables, you can compute covariances among them. If you have two random variables, x and y, then there's only one covariance you can form between them, and that is the expectation value of the product of x minus its mean times y minus its mean. If you have more than two random variables, then you can define a whole covariance matrix, C, whose components are the covariances between the ith random variable x sub I and the jth random variable x sub j, and the definition is just the same one above, but now we use x sub I and x sub j for the two random variables. So you see that here in the case of 2, although I said that there was only a single number covariance, it's actually a little 2 by 2 matrix because it has diagonal elements where we put x on both of these terms, and that will be the variance of x. Or if we put y, we'll get the variance of y, and if we put an x and a y, we get the cross term. And of course the matrix is symmetric because the product of this x term times this y term is the same as the product in the reverse order. So that all generalizes here, and you see that the covariance matrix is a symmetric matrix whose diagonal elements are the variances of the individual variables, and the off-diagonal elements are the cross covariances. Now suppose you have a bunch of random variables, and for whatever reason you are interested in a particular linear combination of them. So that's a sum with some coefficients that you're given, alpha sub I times x sub I. So this is itself just a random variable, and you might wonder what its variance is. So let's compute. The variance of this linear combination is the expectation of the square of its value minus its mean. In other words, the sum over I, alpha I times x sub I is our random variable. The sum over I, alpha sub I times x sub I bar, the means of the separate components, are the means of our random variable, and therefore one factor in the second moment is this thing. And I repeat that factor a second time to make it the second moment. And now let's see, what can I do? I can bring both of the sums outside to make it a sum over I and j. And I can bring the angle brackets inside until they cluster around the only things that are random variables, RVs, in this. And you'll see that I have left an alpha sub I on the left and an alpha sub j on the right. And this, if I write it in matrix notation, is just my vector of coefficients transpose times C, the covariance matrix that I defined up here, times alpha. In other words, it's a quadratic form involving alpha and C. This also, by the way, shows that C must be positive definite, because this is manifestly a positive quantity because it's the expectation of a square, and this is a general quadratic form because it has a general vector alpha on both sides, and therefore C is a positive definite matrix. We've commented on that before, but we haven't proved it. Since it's a positive definite matrix, we can visualize a covariance matrix as an ellipsoid in a high-dimensional space, where the directions are the different linear combinations of the basis random variables, the x sub I. Now the linear correlation matrix, so-called, is very closely related to the covariance matrix, and here's the relationship. If you have a covariance matrix between some random variables, the Cij, and you just normalize it a little bit differently by dividing by the square root of the diagonal elements in the ith and jth position, then you get a linear correlation matrix, so-called. You often see this formula written out in the case of two random variables x and y as this formula for the linear correlation. Linear correlation matrices are useful because in p-value tests, a very frequent test you want to make is against the null hypothesis that two random variables x and y are independent random variables. And in that case, R is a useful p-value statistic. It's a test for correlation. And what makes it useful is, first of all, when you have large numbers of data points, so you have a long list of x sub i's and a corresponding long list of y sub i's, for large numbers of data points, you can prove pretty easily that R is normally distributed with zero mean and standard deviation as shown here, 1 over the square root of the number of data points. This is essentially the central limit theorem, or a result that follows easily from it. And a consequence of this is that r times square root of n, so I scale this up by the value of the standard deviation, is a normal t-value. In other words, r times square root of n has mean 0 and variance or standard deviation 1. Now, if the number of data points is not large, this is still a useful p-value statistic if the individual underlying distributions are multivariate normal. So the setup in this case would be your vector of x's and corresponding vectors of y would not be so large, so long, as to make the central limit theorem apply. But if the x's and y's are multivariate normal, then there's also a simple form for this p-value, and it's a student t distribution. Finally, there's a trick that was invented by Spearman, and that trick is if you take your vectors of x's and sort them so you replace each value by its rank. So if the vector is of length n, you replace the individual numbers by the integers from 1 to n in ascending order according to the ascending order of the individual elements in x. And then correspondingly, the corresponding elements in y, you replace each value by its rank. And now you compute the linear correlation coefficient, and if you think about it, this is a universal distribution. It doesn't matter what the underlying distribution of the x's and y's are, because you replace that distribution with the distribution of ranks, and the distribution of ranks is exactly uniform because it goes uniformly from 1 to n. So this is called a rank correlation coefficient or a Spearman correlation coefficient. So now we can apply this to that funny looking plot of the exon length data, and we'll easily show that this correlation exists and is highly statistically significant. Here it is in MATLAB. Here's the formula for the coefficient of correlation. You can see it's just copied from the formula on the previous page. And here's the t-value as advertised, and MATLAB works it all out, and here is the matrix of t-values. Now the diagonal elements are the certainty with which we're sure that elements are correlated with themselves. Well, we know that elements are correlated with themselves, and this number will just get larger and larger as we have more and more data. But the interesting numbers here are the t-values for the cross correlation, the correlation between the first exon here and the second exon here. And here you can see we get a t-value of 12.15 standard deviations, which is a huge value. And we're in the central limit theorem limit, where the t-value can be converted to a p-value according to a normal distribution. It turns out that MATLAB has a built-in for this that can return not just the coefficient of correlation, but also the probabilities, the p-values associated with that. And you see 12 sigma is so large that the p-values underflow at 0. It's of course a symmetric matrix, 0 meaning essentially infinitely significant. I'm not sure why MATLAB prints 1s here on the diagonals. That seems a little bit strange, because the certainty with which something is correlated with itself should be completely certain, and therefore the p-value there should have been printed as 0. Clearly some MATLAB person got the convention wrong.